This is for Econ 2302 microeconomics students. This video here is about one of our two consumers utility models. This is a Unit 2 video. So if we're still on Unit 1, don't watch this video. Wait until after we start Unit 2. We've got two different models that are out there that are used to explain and model consumer behavior. One of the things we talk about with consumers is they try to maximize their total utility, stay within the limits of their budget. Utility is defined as usefulness or satisfaction that's received when a product is consumed. The problem is, of course, goods cost money. People have only so much money to spend. And so the question is, how does a consumer maximize his or her total utility, yet remain within the limits of their budget? Well, we have two models for this, and this is the first one. It's called the Indifference Curve-Budget Line Map. If some of you all had pre-calculus or calculus or maybe some geology or geography, some of this is going to resemble some level curves, topographical maps you've seen before. This is an analytic geometry model. It's highly esoteric, meaning it's fancy, it's really analytical, but it's not very practical. The second model, which will be in another video, uses a table, is much more practical and is much more realistic. But we're going to start with this one first because it's actually kind of easy. So let me go ahead and share the screen. We're going to go to the slideshow first, and then we're going to go to a practice problem. Alrighty. So, consumer theory. Production, market structures, and firm choices is the total topic for Unit 2, but we're not dealing with the production market structures just yet. We're dealing with consumer theory. Two models. We're working with the Indifference Curve-Budget Line Map. The tabular approach, means using a table, will be next video. Now, the Indifference Curve-Budget Line Map, as I said earlier, is analytic. It's based on the following math problem. You have a function that uses two variables, and you're trying to find a restricted maximum, like the variables have only so much values they can take, like they're between 0 and 10, 0 and 20. And so what combination of the two variables will maximize the function's value, but stay within the limits of those boundaries for the variables? The model itself is designed to determine how one consumer chooses a combination of two very different products in order to maximize total utility, yet remain within the limits of their budget. So let's move forward then, shall we? Anytime you build an analytic model, you have to have some foundational assumptions, and so we have four of them. Assumption number one, this consumer has preferences that are defined by the following statement. It's better to have more of something good than less of something good. Would you rather have 3 cheeseburgers or 1 cheeseburger? This person wants 3. Would you rather be on vacation for 5 days or 7 days? Well, of course they want 7 days. So the thing is, this person's notion is more of everything is better, less of everything is not so great. Second assumption is the consumer has a budget restraint. They have only so much money available to spend. Now, this model here does not allow for borrowing from your mom or your buddy. It doesn't let you use a credit card or take out a loan. If it's stated this person only has $25 to spend on this activity during this time frame, they can't spend more than $25. It is not feasible to do so. Now, the third assumption is the consumer is going to act according to rational self-interest. That means maximize their total utility, but not exceed their budget. It's reasonable to stay on budget, but it's also reasonable to try to make yourself as happy as possible within those limits. Last but not least, to keep this simple so we can model this on a flat graph, we're going to assume only 2 products. Trying to do 3 products makes a 3-dimensional surface, which is hard to construct on a flat surface like a computer or a board. And once you get beyond 3 dimensions, well, it becomes mathematically and visually unwieldy. So we've got 2 different products. We'll call them product A and product B. And these products, please note, they are not close substitutes of consumption, nor are they strict complements. Folks, substitutes of consumption, close substitutes, are going to have linear indifference curves, and that's not what we're working with. Most combinations of 2 products aren't that. Strict complements produce L-shaped indifference curves with a sharp corner, and because you have to typically consume them within fixed parameters or fixed proportions. And again, that's a very narrow model. So we're dealing with products that are not strictly complementary, and they are not close substitutes of consumption either. And so this leads us to something called the indifference curve map. Now, a couple of things to note. Vertical axis is quantity of product A. Horizontal axis is quantity of product B. Where's the dollar sign? This isn't a supplier demand curve. This is a consumer's map showing combinations. Class, every point you see here has a certain amount of product A and a certain amount of product B. We've also got these 3 indifference curves. Each indifference curve represents a specific level of total utility. So the thing is, on indifference curve U1, any point In other words, any combination of the two products that is on Indifference Curve U1 is on the same level of total utility. If you've ever seen a topographical map like in geology or geography, you have these level curves that represent altitudes above sea level. You could be at two different points on a particular hill, but if they're on the same level curve, they are at the same altitude above sea level. So combination Y and combination W aren't the same combination. Y has a lot of A, not much B. W has a lot of B, not much A. But since they're both on Indifference Curve U1, they have the same amount of total utility. TU stands for total utility. Second property is they're parallel, meaning they don't cross each other. If they did cross each other, then you'd have one combination with two different values of total utility. That can't happen during a short-run fixed time period. Not possible. The third property is that curves that are further away from the origin are preferred by this consumer over those that are closer in. The reason why has to do with the fact that if you go to corresponding points, so please take a look at X and Z. X and Z are at similar positions on two different indifference curves, but if you take a look at X and see how much A and B it has, and compare that to letter Z, or combination Z, pardon me, combination Z has more of product A and more of product B than X, so this person, of course, will be happier with that. Now, they're convex with respect to the origin, meaning that the curve is bowed in or curved in, pointing towards the origin. Some of this has to do with the fact that these products are neither close substitutes in consumption nor are they complementary goods in the strict sense. And plus, when they bow out from the origin, it produces a property where there's a slight positivity in some part of the deal. And no, you have to trade off. If you're going to maintain constant utility, you have to give up some of one good to get more of the other and maintain constant utility. So they can't curve away from the origin. That's also why they're negatively sloped. Again, to maintain constant utility, you have to give up some of one product, get more of the other to keep the utility at a constant level. Now, last but not least, between every two indifference curves is another indifference curve, but we're not going to show them all because there's an uncountably infinite number. All possible combinations of the two products are on some indifference curve somewhere. We always show a discrete, meaning countable, finite number of indifference curves because some types of products aren't divisible into smaller amounts, and also because it makes it easier to see. And once you get too far beyond the budget line, there's no point in showing that indifference curve. So we've got these three here. Now, as we go up here, the next thing I need to mention here is the concept of analysis on the margin. This was mentioned in chapter 1, but the thing is, we do a ton of this in microeconomics. Macroeconomics tries to do this, but marginal analysis fails and blows up and doesn't work in macro because there's too many variables that you don't have control over. And so marginal analysis is really worthless at the macro level. But on the micro level, where there's fewer variables and you have some control of some of them to a strong degree, marginal analysis works extremely well here. The term marginal has several meanings. It can mean a rate of change. It can mean the slope of the line or a slope of a tangent line. And for those who've had pre-calculus or calculus, a first derivative. For those of you who don't know what that is, a first derivative of a function is able to find the instantaneous slope of a curve at a single point or the slope of a line that is tangent to a curve at a point. The word tangent means the line and the curve touch each other. It's similar to an intersection, except the curve arcs away from the line and never crosses the line, but they have that one point in common. The words marginal in English means an additional amount of one thing resulting from or coming from an additional amount of something else. Like if I spend one more dollar, my total utility goes up this amount, stuff like that. In microeconomics, we'll be doing marginal analysis out the wazoo the entire rest of the course, so you have to be aware of what marginal means. Now, this leads us to a concept called the marginal rate of substitution of the two products. The marginal rate of substitution of one good for another is the measure of the number of units of one good, I should say, the consumer is willing to give up in order to get one additional unit of the other. It's like a trade-off between two products here. And the thing is, it is defined on a technical level at a specific point. It is contingent upon how much you have of each product. Folks, when I was in college at UT Austin, freshman year in Jester West, there was these coupon books where you get discounts off this local pizza place, and you could order 2 medium, 2-topping pizzas and get 2 cans of soda for $10. And so if you had about $12, you had enough money to pay the tax, tip the driver. It was a pretty good deal. The only thing is, income tends to be scarce for college students, and you might order this deal, and when you get the pizzas and the sodas, you realize, you know what, I've got 16 slices of hot pizza, but only 2 cans of soda to wash it down. And so the thing is, you want to have some more soda, you might have to knock on a few doors and see if somebody has some extra sodas in their mini fridge, if they're willing to trade slices of pizza for soda. The thing is, 2 cans of soda with 16 slices of hot pizza means you're very likely to be willing to give up 2 or 3 slices of the pizza to get 1 more soda. Reason: you have an overabundance of pizza and a dearth or a lack of soda. But suppose the guy messed up the order and the person didn't pay attention. They realized, wait a minute, I've got a 24-pack of soda and just 2 slices of pizza. That's a different situation. That person probably would not want to give up any slices of pizza for more soda. Or if they gave up even 1 slice of pizza, they'd expect maybe a 12-pack of soda in exchange for it. You have to understand the desire to trade off between these 2 products is dependent on how much you have of both products. And that's why the marginal rate of substitution, MRS, of product A in exchange for product B, or vice versa, product B in exchange for product A, is evaluated at a single point at that combination. Now, we define that as the slope of the line that is tangent to the indifference curve at that point, at that combination. Now, if you take a look here at point or combination Y, it is given by me that line L1 is tangent to indifference curve U1 at point Y. And so the slope of line L1 is going to be equal to the marginal rate of substitution of product A in exchange for product B at point Y. One little quick comment. Notice the product that is being given up is small and down on the right. We call that a subscript. The product that is being received in exchange is large capital on the same line as MRS. Okay? Now, the thing is, if you were to do the slope of that line, you would find it's the change in quantity of A divided by change in quantity of B, and that is, by definition, the slope. Now, if suppose we wanted to flip this here, and I'm using that term very specifically, I might add. If you want to flip this and give up B and get A, that's called the MRS of product B in exchange for product A. That's how many units of product B the consumer will give up to get 1 more unit of A. That is going to be equal to the reciprocal of the slope of the line that is tangent to the indifference curve. Since line L1 is tangent to indifference curve U1 at point Y, the reciprocal of the slope of line L1 is equal to the marginal rate of substitution of product A in exchange for product B at point Y. Do not say inverse. There are 2 inverses. There's additive inverse and multiplicative inverse. This is the multiplicative inverse, which is properly called the reciprocal. So you need to be aware of MRS of A for B or B for A at a single point. MRS of A for B, slope of the tangent line at that point. MRS of B for A, the reciprocal of the slope of the tangent line at that point. Now, the thing about the indifference curves is they model what the consumer prefers, what they would want, what they would like to have, but we have to deal with the money, how much they have to spend, and that's where the budget line comes in. The budget line is the set of all possible combinations of the 2 products that this consumer can afford if they were to spend all the income. Now, class, a couple of comments here. P stands for price. You should already know this. P subscript A means price of a unit of A. P subscript B means the price of a unit of B. And that is not a number 1. That's a capital I. Capital I, you should already know from the E sub I coefficient, stands for income. And so the thing is, these 2 endpoints, the one that's on the vertical axis, the consumer is spending all their income on product A and buying 0 units of product B. Over here on the horizontal axis, the consumer is spending all their income on product B and not buying a unit of A. So if product A costs $2 and you have $20, you can buy 10 units. If product B costs $4 and you have $20 to spend, you can buy 5 units of B. But notice in each case, we're buying none of one and spending all of our money on the other. So when we connect these 2 dots here, we get all these possible combinations that are going to cost exactly the income. We call this triangle here the feasible region. Now, some of y'all should probably remember doing linear inequalities. You're trying to figure out if something is greater than or less than. You figure out which side of the line do you shade, and this includes the full amount of monies. That's why the line is solid. You have to figure out what combinations will cost less than or equal to the full income. Well, 0 of each one costs $0, and so that's less than the income. And so we would actually shade in this whole triangle to create what's called the feasible region. That is defined as the set of all the possible combinations of the 2 products the consumer can afford, just afford. They don't have to spend all their income for the triangle if it's below the budget line. On the budget line, they spend all their income. So that means anything over here above the triangle where I'm moving my pointer is unaffordable, too expensive. They can't buy it and they can't borrow. Now, we have to calculate an equation of the budget line, and here's the formula for that. QA and QB are the variables of the formula. So when you calculate that equation, they remain QA and QB. In these problems, you're always given the income, the price of product A, and the price of product B. Now, y'all should have noticed already this line has a negative slope, hence the negative sign over here. The first term in the equation, this is the slope of it, is negative price of B divided by price of A. If you want to derive this using the slope formula, those 2 points, knock yourself out, but I'm just trying to give you the formula to have you calculate it directly. So negative price of B divided by the price of A times the quantity of B. That's the first term. And then the vertical intercept, take a look. The vertical intercept is income divided by the price of A. These are two separate terms. A plus sign separates them. And so we have a little example. If the consumer has $20 to spend, the price of product A is $4 a unit, and the price of product B is $2.50 per unit. The budget line equation would be set up first by plugging in the 2.5 over 4, the dollar signs factor out by factor label rule, and then the 20 over 4 for the income divided by the price of A. And then we simplify the slope to a fraction. No decimals, remember, fractions only. And so we factor 50 cents out of the top and the bottom. We get negative 5/8 for the slope, and 20 divided by 4 is 5. So the full budget line equation from start to finish is QA equals negative 5/8 QB plus 5. Now, determining the optimal combination. Remember what we said about the assumptions. This consumer wants to get the most utility possible. That means they have to be on the farthest out indifference curve possible. That does not exceed the consumer's income, meaning it has to be on or inside the feasible region. So if you look at what we got here, combination X is on a farther out indifference curve than W or Y. Combination X, therefore, has more utility than W or Y. Combination Z has even more utility than X, but it's not on the triangle. It's not inside the triangle, so they can't choose combination Z. It's not affordable. Combination W, there's money left over since it's below the budget line. They could spend a little more money and buy combination X and be happier. Combination Y costs the same amount of money as combination X, but combination Y, the situation there is it's too much product A, not enough product B, and that's why it is lower utility than combination X. Some of y'all say, well, how do you know that? Well, look at how much A has. Look at how much B has. Look at the vertical coordinates where they'd be. Y has more A than X has. Look at the horizontal coordinates. That's how much B Y has. Here's the amount of B X has. That has very little B and a lot of A compared to X. And so for this particular consumer, combination Y is not preferred. It's too much A, not enough B. The thing is, this is the chosen point. Last but not least, the marginal rate of substitution at that chosen point would be the slope of that budget line, negative PB over PA, and you plug the numbers in. The MRS of B for A would be the reciprocal of that slope of that budget line, or negative PB over, or negative PA over PB, excuse me. Now, let's put this all together and look at a sample problem. This is not the same problem we had here in that slideshow, and we've got information given. This here is a local pizza parlor, meaning if somebody in the kitchen messes up and cuts the pizza irregularly where some slices are larger than they should be and some are smaller, the manager or the owner could say, you know what, this is half of a size of a slice of pizza, we'll charge half the price, or it's 2/3 the size of a slice, we'll charge 2/3 the price. Similarly, their beer distributor might have actually delivered a 6-pack of Stubbies along with the regular bottles they got. And so since Stubby bottles only have 8 ounces as opposed to 12 or 16, they're going to sell the Stubby bottles at a lower price or sell them for like half or a fourth or whatever the price. So the 7.5 bottles of beer and 2.8 slices, that's how you can have that. Now, let's take a look at these. Which point is chosen? Which point is on or inside the triangle, yet is on the farthest out indifference curve? Combination W, it's maximum utility within the budget. For each point that is not chosen, why not? Take a look at X. X is too expensive. 8 times 2 is 16. 5 times 5 is 25. 16 plus 25 is $41. They have only $20 to spend. X is too expensive. It's also on an indifference curve that is outside the feasible region. Combination Z is not enough of either product. It is possible with Z to spend some more money, in this case buy 2 more bottles of beer, and the consumer will be happier with W than they will be with Z. So it's possible to spend more money and get more utility. Now take a look at Y compared to W. Y has fewer bottles of beer than W, so it's not enough beer, not enough product A, or actually, and then on the other hand, Y has got more slices of pizza than W. It's too much pizza, not enough beer for this person's taste. The flip side with V. V, you'll notice here, has got more beer. It includes that little stubby bottle, but it also has less pizza. V, it's too much B, not enough A. Too much pizza, not enough beer. And so out of all of these, that is the chosen point, okay? Now, let's talk about the budget line equation. Again, just a quick reminder to everybody here. The formula says QA is equal to negative price of B over price of A times QB plus income times the price of A. So I'm going to borrow this here and insert this into this Word document, and we're going to go ahead and solve for this. Now, notice you're given price of product A, price of product B here. The slope is negative PB over PA. Well, that's $2 over $5. That's going to be a very easy reduction for us. $2 divided by $5. Let me zoom in here just a wee bit here because I'm having a little bit of problems with the controls here. Okay. We're going to replace the price of B with $2, but that's going to factor down to 2, and replace the price of A with $5. So that's going to be replaced with a negative 2/5, excuse me. Now, income, it was said it equals to $20, and the price of A is $5. What's 20 divided by 5? That should be an old times table problem. Yeah, 20 divided by 5 is simply 4. So we replace that whole thing with 4. So your budget line equation here, using that formula, remember the QA and QB are the variables of the formula, is QA is equal to negative 2/5 times QB plus 4. All righty. Now, part D asks 2 questions. The first question it asks is, what is the marginal rate of substitution of product A in exchange for product B at the chosen point? And they want it both in concept and in a numerical answer. All righty. Well, MRS of A for B, we've already said, is the slope of whatever line is tangent to the chosen point. And what's the name of that line that's tangent to the chosen point? I'll give you a hint. We just calculated its formula. That's right. It's the budget line. So the slope of the budget line is the concept answer. At the chosen point, the marginal rate of substitution of product A in exchange for product B is the slope of the budget line. What's the numerical answer? Well, let's take a look at this. This is in slope-intercept format. Vertical variable equals slope times horizontal variable plus vertical intercept. So the slope is the coefficient on QB, and so that means the MRS of A for B is equal to negative 2/5. So let's go ahead and write this down. MRS of A for B, and I'm going to go ahead and let's see. Bear with me for a moment while I make some adjustments here. I am a fan of Times New Roman. Yes, some people say it's a boring font. I like it. Okay. And we're going to make this a subscript here. So font. And see, you're learning a little bit of Word while you're at it along the way. Okay. We're going to make this a subscript. Okay. MRS of A for B. Okay. Equals concept slope of the budget line equals, and then numerical, we're going to go to insert, and we're going to insert a math object here. We're just going to make the negative 2/5 in there, just so we have something that we can see. Okay. Again, you would obviously be writing this by hand, okay, because this is a handwritten homework assignment. This is not by any means something for y'all to do with Word. Okay, what in the world? I'm trying to get that number in there. So 2. Okay, well, don't you just love it when computers don't cooperate? I'm going to do it this way here. Okay, for now. Negative 2/5 is the MRS of A for B at the chosen point. Now, suppose I were to flip this. Suppose instead I had asked, what is the MRS? Excuse me. That's not what I was trying to paste. If I instead asked for the MRS of B for A, would that be the slope of the budget line? No, it's the reciprocal of the line that is tangent to the chosen point. So that'd be the reciprocal of the slope of the slope of the budget line. Now, what would the reciprocal of -2/5 be? Well, first of all, a negative number has a negative reciprocal. You never drop the sign from a negative number when you make its reciprocal. All that the reciprocal says is swap the numerator and the denominator. And remember, if we had a whole number, that would make the denominator the invisible number 1. So we're going to put the -5 in the numerator and the 2 in the denominator. And so the marginal rate of substitution of product B in exchange for product A is the reciprocal of the slope of the budget line, and that is equal to -5/2. Again, that was not asked in the problem, but I was trying to come up with a way here to show it to you here, because what if I did ask it? I could ask for either. It's in bounds. All righty, we're going to stop sharing now. We're going back over here. Okay. This is actually a very quick, easy problem. In fact, it's one of those so-called 5-minute problems that usually shows up on a test every now and again. It's kind of very esoteric and very highfalutin in its concept level, but once you know what the stuff represents, it's lickety-split fast to solve. So this is my video on this topic here. I hope it helps out. Y'all have a great day, and thank you very much. Make sure you post your comments and indicate you took notes. Have a good day.